Okay, so so we continue with the analysis of the free boundary problem. So I gave a little bit of the background just a moment ago, and I will mainly focus on the one fluid case. And then the first thing is to do some very simple calculation and understand the pressure and the role of the pressure in the problem. So if we look at the pressure in the Euler equation, if we take the divergence of the equation, again, we get the same Poisson equation. I did not put the summation there, but the convention is that whenever you see repeated indices, they are summed. But I can put it there. And then that's the same Poisson equation. But in the fixed boundary case and the free boundary case, and with or without surface tension, they make a huge difference. In the fixed boundary case, then you can assume that the boundary is smooth, and assume the no slip boundary condition. And then, as explained like half an hour earlier, the pressure has the same regularity pretty much as the velocity field. And the gradient of the pressure, which is the Lagrangian multiplier in the Lagrangian formulation, appears like a driving force in the Euler equation at the same regularity level as the velocity. So that does not make things worse. And it also helps the Euler equation to appear as an ODE in the Lagrangian formulation. But in the free boundary problem, when you the free boundary itself is moving, and the regularity itself is an issue, then we know that without surface tension, the pressure is equal to 0 on the free boundary. So if you combine this boundary condition and the Poisson equation, then you see that the pressure, usually when you solve the Poisson equation, the pressure should not be more than half derivative better than the regularity of the boundary. Or it should not be after you take the gradient, then the regularity of the gradient of the pressure is no better than the regularity of the boundary minus 1/2. Okay, and at the same time, it should not be better than the regularity of the velocity. With the surface tension, then we know that the pressure on the boundary is equal to the mean curvature of the surface, and the mean curvature of the surface is like the second order derivative of the surface. So after you take after you take the gradient of the pressure, then the regularity of the gradient of the pressure is no better than the regularity of the boundary minus 5/2. So that's much worse. And also it shouldn't be better than the regularity of the velocity field. So putting all of these things together, it looks like it's a little bit mysterious that the surface tension is supposed to be a good factor to help stabilize the problem and to help the problem to improve the regularity. But with the surface tension, the pressure becomes much worse. Okay, without surface tension, it's better, but still it's problematic to handle it. Because in either of these cases, you can really think of the gradient of the pressure as a driving term. Especially when you restrict it to the boundary, the regularity of this term is worse than the boundary regularity. So one has to figure out a better way than treating it as a driving force as in the fixed boundary problem. So one needs to figure out a correct way or reasonable way to treat this, to identify the structure to handle the related regularity issue. And so, as we said, that the surface tension is a physically stabilizing force. It's supposed to regularize the boundary, but somehow from the regularity analysis of the gradient of the pressure, it caused lower regularity of the gradient of the pressure. So how do we make this up? That's the same question I was talking about on the last page. And also, if we consider the Lagrangian coordinates, if you think about the Lagrangian coordinates and the boundary evolution, then it looks like, because the boundary is transported by the velocity, and the velocity restricted to the boundary, is basically the velocity regularity minus 1/2 in the interior. So this gives you the regularity of the boundary if you just follow the Lagrangian coordinates. That's not good. If you take this and combine it with the regularity counting of the gradient of the pressure, it looks even worse. So how do we close all of these regularity counts? So again, if we think in a slightly different way, go back to the Lagrangian formulation instead of sticking to the Eulerian formulation. So in the Lagrangian formulation, first we still look at the Lagrangian coordinates with the same definition, that is the particle path in the free boundary problem, following the velocity field coming from the Euler equation. And this time the configuration space is slightly different. It's not a group anymore because here we only have the volume preserving constraint and it has no more constraint that it maps to the boundary to the boundary. So apparently this is not a group, but this is still the set of volume preserving maps. One can intend to think this is still infinite dimensional manifold because it's a subset in the infinite dimensional space with how many constraints? Infinite many constraints, because you have to compute the determinant at every point. Okay, but still this would leave infinite dimensions. So somehow conceptually this is the infinite dimensional space. At this moment, we're not going to the extreme rigor to prove that this is a manifold in the infinite dimensional space. This was done for the fixed boundary case, but right now we're not going to do that, but just stick to the formal thinking. In the fixed boundary case, we didn't need that in the analysis because we really used the Lagrangian formulation to construct the unstable manifold. So everything was done rigorously over there. But here, let's just think formally that this is a manifold in the infinite dimensional space. And then this is the configuration space. The tangent space of this configuration space is given by divergence-free vector fields when you compute the divergence in the Eulerian coordinate. Okay, so W is given in the Lagrangian coordinate. You see that here, the domain of these things are the original domain, the initial domain at the time t is equal to 0. So this is the Lagrangian domain. And so W is defined in the Lagrangian domain, and this is a variational vector field. So if you compose with U inverse, you get back to the Eulerian domain, then you take the divergence should be 0. Okay. And again, from the same reason, the kinetic energy comes from the L2 norm of the velocity field. So it's natural to impose L2 metric on the tangent space and the ambient space of the configuration manifold. So if you look at if you equip this with the L2 metric and embed this into the L2 space, then look at its orthogonal complement. This tangent space is actually bigger than the tangent space in the fixed boundary case because there is no non-slip boundary condition. So this is a bigger tangent space, then its orthogonal complement is smaller. The orthogonal complement is given by L2 gradient vector field in the Eulerian coordinates. So that the potential function has 0 boundary condition. So this is needed to make this orthogonal complement of the divergence-free vector field. So in the same way, you can write the Euler equation in the Lagrangian coordinates as the second order derivative of the Lagrangian map is equal to the pressure. Okay, basically this is equal to the pressure. But this time the pressure on the boundary, for example, when there is surface tension, the pressure on the boundary is equal to a constant times the mean curvature. So this may not be equal to 0. When this may not be equal to 0, then this term may not be in the orthogonal complement of the tangent space. Okay, so the UTT this time may not be a normal vector to the infinite dimensional manifold. So the Euler equation is not the geodesic flow when you have surface tension. Okay, that's different from the fixed boundary problem we saw. And so we need to think of this more carefully. So again, let's look at the energy conservation. Multiply the Euler equation by the velocity and integrate. You see there is a conservation law. The conservation law is the kinetic energy that's velocity squared, integrated. And there is a potential energy that is the surface area of the free boundary. So here S is the surface area. And so this is the total energy. So there is a kinetic energy and there is a potential energy of the surface area. This is actually, so when we take the Euler equation and derive the conservation law, physically probably it's the other way around. When you, one could set up the energy and the Lagrangian and derive the equation. Okay, so in the Lagrangian coordinates, so this is computed in the Eulerian coordinate. In the Lagrangian coordinate, then the velocity square is same as the time derivative of the Lagrangian map squared, because the coordinate change from the Lagrangian to the Eulerian is volume preserving, so there is no change in the volume element. So this is the kinetic energy. And the potential energy right now becomes functional depending on the configuration map, the Lagrangian map at this moment. So if you know U, then you map the original boundary, the initial boundary, to the current boundary, then take the surface area. So this is the surface area functional depending on the Lagrangian map U. Okay, but this functional, this is a nonlinear functional. This functional depends on U in a way that it depends on the set. So here I shouldn't have this S. It depends on this set, the physical boundary. It does not depend on the parameterization. So it does not depend on how U maps the original boundary to the current physical boundary. It only cares what's the area of the current boundary, and how the parameterization, how the Lagrangian map behaves doesn't really matter. Okay, so this is conceptually very important later on. Then starting from the energy, the conserved energy, one can perform the Lorentz transformation again, as in the recipe, standard recipe in the Lagrangian mechanics. Then you get the action, the Lagrangian. The Lagrangian is simply the kinetic energy minus the potential energy right now. And yeah, the Lagrangian is defined on the tangent bundle of the configuration manifold. And then you have the action as the time integral of the Lagrangian. So you just think of this or formally at this moment. Then the Euler-Lagrangian equation of the action, that is the equation satisfied by the critical path of the action. Right now, you have the variation coming from the kinetic energy, you get UTT, the second order derivative of the Lagrangian map, and also the variation, did I have alpha? I should have written alpha here. And so then the variation, the gradient of the surface area functional, but here the gradient is only taken on the configuration space. So this is a tangent vector. And then there should be, the combination of these two should be only a Lagrangian multiplier for the, in the Euler-Lagrangian equation. So this comes from the variation of the kinetic energy. This comes from the variation of the potential energy. Okay, and this might contains a normal component. So the whole thing combination is equal to a Lagrangian multiplier. Okay, again, as we view the surface area, functional as from M to R, and so this S prime is a tangent vector on of the configuration manifold. And the Lagrangian multiplier is a normal component, is a normal vector in the infinite dimensional space. As we know that when this is a normal vector, then it takes the form of the gradient in the Eulerian coordinate with a potential function equal to 0 on the boundary. And if you take this Lagrangian multiplier, the normal component, away from the second order derivative, then the second order derivative becomes a covariant derivative. So you have dt ut in the covariant derivative plus the gradient of the potential energy is equal to 0. So this is a new Euler equation in the problem with surface tension. So when the problem has surface tension, it's not a geodesic flow anymore. It is a Lagrangian flow with a potential energy. When there is no potential energy, when there is no surface tension, this is still a geodesic flow. Okay. And then we also know that the action, so if we come back for 1 second, look at the Lagrangian. Look at the Lagrangian here. If we apply, if we think about L of U composite phi, and phi is a relabeling transformation, and then W also relabel in the same way. Here, where is phi? Phi is in the volume preserving, phi is a volume preserving transformation associated to the initial domain. Okay, so if in the initial domain you relabel the particles in a volume preserving way, this is volume preserving and it maps the boundary to the boundary, then the Lagrangian doesn't change, the action doesn't change. So here you have a symmetry. The same group as in the fixed boundary case, that same Lie group acts on the Lagrangian here invariantly. So this action is invariant under the action of infinite dimensional Lie group. And so you have infinite dimensional conserved quantities. And this, again, is related to the transport of the vorticity. And then this gives you the kind of like estimate of the you can get the estimate of the vorticity by using the transport equation. But of course, you don't have to know all of this to estimate the vorticity, but it explains. And not only it explains, it gives you a way to recover the rotational part of the velocity field without the simple connectedness assumption. Okay, as we said, the Lagrangian multiplier in the problem is the gradient of a function which vanishes on the boundary. And you can compute that it satisfies the Poisson equation here. And then how about the other term, the gradient of the surface area functional, which is a tangent vector. So this turns out to be also a gradient vector field. But of course, the boundary value is not 0. Boundary value of P tilde is not 0 anymore. Otherwise, that would make it a normal component, a normal vector. This is indeed tangential. And it is a harmonic function. The potential function is a harmonic. So it's divergence, the gradient of P tilde is divergence free. It's a tangent vector. And on the boundary is equal to the mean curvature. So this can be computed easily by first taking the area variation of the area, then the mean curvature comes out. Then after the mean curvature comes out, that's a boundary integral. And you want to make it into the interior with the L2 duality. Then that gives you this form. Okay, exactly this form. So now if you put these two together, so here, this is a calculation leading to the above. So if you do the area variation, if you do the area variation with respect to a divergence-free vector field. So first, the area variation tells you that this is equal to, on the boundary, you have the mean curvature times the vertical component of the variational vector field. Then you take the mean curvature, take the harmonic extension to the interior, and take the gradient. And you get this form. That's here. So the pressure now is actually the sum of these two parts, P0 and P tilde. One comes from the Lagrangian multiplier, and one comes from the variation of the surface area. So the total pressure in the Euler equation with surface tension, in fact, is not simply just the Lagrangian multiplier as in the fixed boundary case. It's a combination of both. And in particular that the regularity of the part of the pressure coming from the surface tension is much lower, not too much lower, but about 2 derivative lower than the regularity of the part coming from the Lagrangian multiplier. So it means that we should not treat the pressure as a single pressure in this analysis. We should split that into 2 parts and handle them separately. And so with this in mind, we start some analysis of the Euler equation by first to do the linear analysis. So with surface tension, let's take the surface tension and then linearize the Euler equation and look at the solution, which is the linearized solution should be in the Lagrangian formulation. Formally, it should be a tangent vector field. It's a variational vector field. It should be a tangent vector field. So that means it's divergence free in the Eulerian coordinate when it's tangent in the to the configuration manifold. Then it's divergence free in the Eulerian coordinate after you composite with U inverse. Formally speaking, if you look at this equation, and do the variation, linearization, and if you believe me for a moment, ignore the Lagrangian multiplier, assuming this is better than the rest, and look at only the left part, then you end up with the second order derivative in W and the Hessian of the potential energy acting on W is equal to some lower order term. Okay, then the key is what is this Hessian of the surface area element? The key of then you do the calculation, you find that it has a principal part. The principal part is a self-adjoint operator with respect to the R2 metric. And for any divergence-free vector field, so this calculation is done in the Eulerian coordinate. So when we say that we think of the problem in the Lagrangian coordinate, but the calculation are mostly done in the Eulerian coordinate, that's much better. Then this operator A in the Eulerian coordinate, it takes the following form. When you look at the quadratic form generated by this self-adjoint operator, because the Hessian is really symmetric. And the surface area involves the first order derivative on the boundary. So when you take the Hessian, it's not a bounded operator. It's an unbounded operator. So it turns out, when you look at this quadratic form, this is equal to, you take the variational vector field here, you apply A to W and W. You take normal component of W on the physical boundary and take the tangential gradient. So this is a scalar function defined on the physical boundary. Then you take the tangential gradient, then square it, integrate. Okay, this is this operator A. So what does this tell us? This tells us that this is bigger than or equal to 0, apparently. And it controls W tilde. No, it controls the normal component of W. And it controls the gradient of the normal component of W. So it controls something. So, but then we are missing the other part of the vector field W. We only have the normal component of the boundary. Even if we know that it's divergence-free, we are still missing a lot. Because, for example, you can have a divergence-free vector field with identically 0 normal component on the boundary. So this operator A controls only some part of the velocity field. So what part is that? That is, we need to carry out a Hodge decomposition of the velocity field. So for on any domain, if you have a velocity field which is divergence-free, then you do the Hodge decomposition. It can be decomposed into a gradient part, which has 0 vorticity, and a rotational part. So both of them are divergence-free. So the rotational part is divergence-free, and it has 0 normal component. So the rotational part is volume preserving, and also it doesn't cause any boundary motion. So it's purely responsible just for internal rotation. Okay. it has nothing to do with the motion of the domain, the movement of the domain. It only controls internal rotation. And so it's determined by just the vorticity. Okay. And the other part, the gradient part, it's also divergence free. So it means that the potential function is a harmonic function. And its normal component is exactly the original normal component. So this part is only responsible of the motion of the domain, and it has nothing to do with internal rotation. And this is an orthogonal decomposition in the L2 metric. Okay, so this can be done following the standard Hodge decomposition procedure. And so now, if we think about here, we have the normal component of the original vector field, and use the normal component, we solve the Laplace equation and find the potential function of the rotational part, and take the gradient of the rotational part. So for example, the tangential component of the velocity, or the velocity potential on the boundary, is determined by the Dirchlet-Neumann operator acting on the normal component, or inverse of the Dirchlet-Neumann operator acting on the normal component of the velocity field. So the Dirchlet-Neumann operator is heavily involved in the free boundary problem here. In particular, if we take initially the rotational part to be 0, okay, that corresponds to 0 initial vorticity, then it tells us a simple calculation from the transport of the vorticity shows that the rotational part will always be 0 in the future. So that's why one can consider the rotational problem. That's from the transport of the vorticity. So with this in mind, then let's look at this operator A, this self-adjoint part, this self-adjoint major part of the Hessian of the surface area functional. So it controls, as we said, it is pretty much the L2 norm of the tangent gradient of the normal component of the vector field. Okay, so the normal component of the vector field is equal to the Neumann derivative, the Neumann boundary condition of the potential function of the rotational part, which is a harmonic function. So phi is harmonic, and the gradient phi is the irrotational part of W. And then when you know the normal component of the irrotational part of the velocity field, in other words, if you know the Neumann condition of the harmonic function phi, then you pretty much have the estimate of the harmonic function phi. Okay, this is wrong. There is no gradient. So roughly speaking, this is, oh no, there is, sorry. This is still gradient phi. Okay, so here this is gradient phi restricted to the boundary, take one derivative. So this here is one derivative, and restriction to the boundary is like half a derivative. So totally, this quantity A controls 3/2 derivative of the irrotational part of the vector field W. Okay, so it does control something, but only the irrotational part. And this is reasonable because this part is the part responsible of the motion of the domain. And A is from the surface area. So that is related to the variation of the surface area. So it has only something to do with the part related to the movement of the domain. And if the velocity field here, if this vector field W is only rotational, it's only like it only causes internal rotation, then the surface area wouldn't change. And so this functional does not act on those kind of rotational vector field. Then it does not have any control at all. Okay, so putting this together, you see that this operator A as a quadratic form controls 3/2 derivative of the irrotational part. In an irrotational problem, so A is like a third order derivative operator. So when A is third order derivative, and you think this is third order derivative, this is two derivative in time, then one time should correspond to 3/2 space derivative. Okay, so it tells us that the velocity compared to the regularity of the configuration, maybe there is a 3/2 difference in terms of the regularity. But one should be very careful because this only acts on the irrotational part of the velocity field. And and also keep in mind, this is the geometric velocity only, geometric velocity of the free surface. It does not control how the surface is parameterized. The same surface can be parameterized in many different ways. So this control is really related to geometric velocity. So it's only related to some geometric regularity, not the regularity of the parameterization. So this improvement of the regularity is only geometric. It does not improve the Lagrangian coordinate, the regularity of the Lagrangian coordinate. So the Lagrangian coordinate is not expected to be smoother than the velocity field. You really solve the Lagrangian coordinate map from the velocity field without any additional smoothing. But the surface, the free surface, can be expected to be smoother, 3/2 derivative smoother than it should be. Okay, conceptually speaking from now at this moment. So this is the first energy estimate we could obtain. That is from the Euler equation, written in the Lagrangian formulation. So it's really a formulation. And then you simply, starting from here, you differentiate, as we always do in the energy estimate, we differentiate the equation many times and multiply it by something and then integrate. The only thing is, how do you differentiate it? You differentiate it according to the structure of the equation. If you really take the space derivative and differentiate, it's going to be a big mess. Well, it worked, I think, for Cotin and Scholar, except it's really very, very messy. We couldn't figure that out. After you write everything in the Lagrangian coordinate and take 3 derivatives, after 2 derivatives, I got lost. So we took a derivative in a different way. We saw that in the linearized problem, this is the leading order space differentiation. Okay, this operator A related to a third order derivative. It's a third order differentiation. And this is the major component in this differential equation in the spatial part. So we use this as the way of differentiation. We apply this operator to the equation many times, enough number of times so that we can do the estimate. So we apply it to the equation. Apply A is pretty much like apply partial t. Okay, so an equivalent way to do it is to take the time derivative of the equation and then do the usual energy estimate. But remember that this operator A only controls the operator A only controls the rotational part of the velocity field. It cannot control the rotational part. So the rotational part is controlled by the vorticity transport. So you need to use the transport property of the vorticity to control the rotational part, and combine them together, you get a closed energy estimate local in time. That gives you, say, suppose the velocity field is in h 3/2 k. So the 3 is from A. A is the third order pseudo differential operator, non-local. And the boundary is 3/2 derivative better. Because if you restrict the velocity field to the boundary, it's 3/2 k minus 1/2 by the trace theorem. Then when you compare the regularity of V on the boundary with the regularity of the boundary, there is improvement of the 3/2 derivative. Okay, and so that is the improvement we saw just over here, that one-time derivative corresponds to 3/2 derivative in space geometrically. So the boundary gets better regularity. But and the pressure you can compute the corresponding regularity. But this improvement is only, again, geometrically, as a surface, this is so smooth, but the Lagrangian map is not. Okay, the Lagrangian map may be much worse, maybe only as good as V. But that's enough, because where do you use this? You use this in the estimate of the elliptic equations, the associated elliptic equations related to, for example, the Diffie-Neumann operator. And when you have enough of the boundary regularity, it allows you to carry out the elliptic estimates. And so the way we did that was really did that in a coordinate independent way. And for example, the regularity of this is estimated on the curvature. We estimate the curvature, we get the estimate of the curvature in H3½ minus 1 on the boundary. And this is given by the Beltrami Laplacian of the boundary, in terms of the Beltrami Laplacian of the boundary. So it's rather intrinsic, and the estimate can be obtained in a relatively clean way, except when you want to do the well-posedness, the construction of the solution. This coordinate independent setting becomes a disadvantage instead of an advantage. It's intrinsic when you do the estimate, but it becomes a disadvantage when you want to construct a solution, because you have to put the different approximate solution in the same framework so that you can take the difference and estimate the convergence. The interface problem of two fluids can be estimated in exactly the same philosophy. So go to the Lagrangian formulation and identify the Lagrangian configuration space. The Lagrangian configuration space will be the space of volume preserving maps on the two domains, so that they share the interface. They share the same interface. And then you impose the R2 metric and compute the surface area and the variation of the surface area and so on. And you will derive operator A in a similar way. And it's still a third order operator, and the rest can be handled. But one thing I want to point out is that in this calculation here, this is three derivative, and other terms are lower order terms, but lower order terms actually involve second order derivatives. So when you have three derivatives in the leading order, second order derivative is not exactly lower order. Anything lower than 3½ derivative is lower order, but the second order derivative is not. So that means, but however, those second order derivatives appear in a self-adjoint way. So they can be handled, they can be incorporated into the leading part of the energy and handled without much problem. Okay, but without surface tension, the situation is a bit different. You have a geodesic flow, and the surface tension disappears, and that operator A disappears. So we have to think of this in a slightly different way. But we still start with the linear analysis. In the terminology of classical Riemannian geometry, linearized solutions to the geodesic flow are called Jacobi fields, and they satisfy this equation. Formally, that's what you expect. And there is this additional operator. This additional operator is the curvature operator induced by the Riemannian metric on the configuration manifold. And the Riemannian metric here is induced by the R2 norm. So with the R2 metric on the tangent bundle of the configuration manifold, there is a curvature tensor. And then the linearized equation, the Jacobi field equation, involves this curvature operator, which is symmetric in W, and it depends on where you linearize. And then one can compute this curvature operator. The curvature operator can be computed, well, let me try you the definition of the curvature operator, but that's not the most convenient way. There is a formula to compute the curvature operator from the second fundamental form. And the second fundamental form comes from the Hodge decomposition. So you compute the curvature operator by using the second fundamental form. And remember, this is symmetric, or you can prove this is actually self-adjoint. Then turns out to be, this is the leading part. Then plus the dots are bounded terms. These are bounded quadratic forms. And this is not bounded because if you take W, as we are using the L2 metric, if W is in L2, again, this is calculation is done in the Eulerian coordinate. Okay. The way is we always think of the problem in the Lagrangian coordinate, but the calculation is done in the Eulerian coordinate. And then you look at the W, if you take W in L2, divergence free. And when W is L2 and divergence free, this makes sense, but it's not in L2. So in order for this quantity to make sense, you need the W perp to be in L2. So you actually want W to be in H1 half. So this is comparable to the H1 half norm squared if W is irrotational. Okay, so this is not a bounded quadratic form. So this is not a bounded operator. This part is bounded, but this is not. So this is, if you count, this is like half a derivative in the quadratic form. So this is like a first order operator, non-local first order operator. If you recall, compare this problem, the geodesic flow on the fixed domain. Okay, for the Euler equation on the fixed domain, it could also be viewed as a geodesic flow on the configuration space, which is the Lie group of volume preserving maps on the fixed domain. Over there, the second fundamental form was a bounded bilinear transformation. So the curvature operator would also be a bounded bilinear, would also be a bounded self-adjoint operator, a symmetric operator for the problem on the fixed domain. But for the problem on the moving domain right now, this curvature operator becomes an unbounded operator. This is really related to what I commented before, that is, the curvature, the Riemannian structure is based on the L2. So we take the L2 Riemannian structure on the tangent bundle of the configuration manifold. This is weaker than the differential structure of the manifold, conceptually. So now, if we think about this problem, and think this is simply the second order derivative in time for a moment. This is the second order derivative in time. And you have unbounded operator here, which is first order in space, like a first order differentiation in space. Then the sign of this operator becomes important. If this operator is negative, you are dead. You would have growth like e to square root kt, and k is the wave number. And then the problem is ill-posed. The linear problem is ill-posed. So you want this to be positive. You want this to be positive. How can that be true? You want this to be positive. So that is the Rayleigh-Taylor sign condition. So the ill-posedness occurs unless you assume the sign condition. So this is the famous Rayleigh-Taylor sign condition. It had been known for a long time in the fluid mechanics, and it was a crucial assumption in all the well-posedness proof. Okay, and so assume that this gradient of the pressure on the boundary satisfies the Rayleigh-Taylor sign condition. So it says that the pressure slightly inside the boundary of the domain is bigger than the pressure outside if there is no surface tension. This is, the pressure is coming from the incompressibility. So with this Rayleigh-Taylor sign condition, and then we can obtain the energy estimate of the Euler equation, the nonlinear energy estimate of the Euler equation. But this time, because the curvature operator is first order, this is first order. So one time is more or less comparable to half of a space derivative. And that's only reflected geometrically. So one time corresponds to half a space. So the velocity field restricted to the boundary is k minus 1/2. And the boundary is k, hk. So you get improvement geometrically for half a derivative. Okay. In this case, The estimate is a bit delicate because this boundary is not much smoother than the velocity restricted to the boundary. For example, if you want to take the normal component of the velocity, restrict this to the boundary, get k minus 1/2. But the normal component of the boundary is only in hk minus 1. So the normal component is already worse than the velocity field itself. So you don't want that. So instead of estimating the velocity directly, we considered a vector field. We created a vector field to consider. This is, we take the mean curvature of the surface and take the harmonic extension to the interior. So solve the Laplace equation with the boundary value equal to the mean curvature. And then you get a harmonic function here, take the gradient. This is a divergence-free vector field. And this almost satisfies the linearized equation, subject to some lower order terms. So this procedure is like when you have a rather nonlinear equation and you want to estimate this, it's a bit too complicated. So you differentiate the equation several times and then do the estimate. Because we go from the domain from the Lagrangian coordinate to the curvature. This is like you take a second order derivative. Or in other words, you take the Bertrand Laplacian of the embedding function. You get the mean curvature. And then you take the gradient, harmonic extension gradient. So it's like after you take the 3 order derivative of the Lagrangian coordinate and then carry out the energy estimate. This makes the problem more quasi-linear than the original form. And then use the structure of that first order differential operator coming from the curvature along with this sign. By the way, so this sign is related to the fact. So if you look at here, when this is positive, it says that the curvature is the curvature is positive in these directions. When this is negative, it says the curvature is negative. We know that on the positive curvature manifold, geodesics tend to not separate too quickly. So there is certain stability associated to that. And when you have negative curvature, even in the classical Riemannian geometry, the geodesics separate exponentially, like on hyperbolic surfaces. And when this is unbounded operator, when you have negative sign here, then the geodesics separate exponentially fast with the exponential rate unbounded when the wave number goes to infinity. And that's the well-posedness. So this is related to the geodesic flow conceptually. Then you can do the same thing without surface tension to the two fluid. And if you do that, you will find that the curvature is hopelessly negative in the leading order. It's going to be a second order operator in the leading order, and it's hopelessly negative if there is a jump of the tangential velocity. So it tells you that the Helmholtz instability is going to happen in the interface problem if there is no surface tension. Okay, so
Chongchun, just a couple of minutes. Yeah,
sure.
So we are very close.
Yeah, I'm close to the end actually. So just to summarize, the surface tension, without surface tension, under the condition of the Rayleigh-Taylor sign condition, we get a half a derivative improvement of the regularity of the boundary above the velocity. And with the surface tension, we get a better improvement. That's what we expect the surface tension to do. Except we had to put it in the right way to get that analysis. And finally, I kept saying that the improvement of the regularity are all geometric. So you get the better regularity of the surface of the interface geometrically and not necessarily on the Lagrangian coordinates. So indeed, from example, here this is an example when you have the moving domain is actually not moving, it's always a disk. So the boundary is a circle. And this is a rotational vector field. And here, the Lagrangian coordinates is not much better than the velocity field. So finally, a few words about, so everything I talked about was the estimate. And then eventually one would like to construct a solution from this framework. And one could do that by basically write the moving surface, because when you do local in time estimate, everything don't move too far away. So you fix a reference domain and write the free surface as graph over this boundary of the reference domain. And then from the estimate, we knew that the mean curvature is something to focus on. So we actually use a modified mean curvature. We use a modified mean curvature to represent the surface. So it's like you recover a function from its Laplacian, along with some other things. And then derive an evolution equation of the modified mean curvature, which involves the irrotational part of the velocity field. And this would give you a quasi-linear wave-type equation with one-time derivative equal to like 3/2 space derivative when there is surface tension. And the rotational part is from the transport property, or the relabeling symmetry. And then you design an iteration scheme and a contraction mapping to get the well-posedness of the solution. This is, so there have been some recent work on the problem when the fixed boundary touch the free surface when there is the angle. So in some recent work on the local well-posedness and a priori estimate of this type of free boundary problem, they adopted this type of framework, the Lagrangian framework, and this scheme of construction to get the local well-posedness with some condition on the angle. So let me stop here. Thank you.
Thank you very much for some beautiful talks. We have time, a little bit of time for questions. So I think there are two ways you can go. Either unmute yourself and just ask, or if you write into the chat, then I will ask it for you. I'm putting up a gallery view here. See that I can see everybody. I'm not seeing any questions now. Can I ask something very naive, Chongchun? Mm-hmm. Yeah. The sign condition on the pressure that you get in the single free interface, yeah? Single fluid free interface, does it have anything, does it have a physical meaning? Like, does it mean somehow the pressure is from the inside onto the surface and the surface holds the fluid back?
Yeah, or, yeah, that's the kind of intuition people had before. That is the pressure slightly inside the interface, the free boundary is bigger than if you think that it's vacuum outside and the pressure outside is 0, and then the pressure slightly inside is bigger, and that holds the water together.
But in it, for example, in a situation where your droplet is not convex, where there are things where it, you know, does it become difficult then, or?
It has more to do with actually the rotational part of the velocity field. If no matter what the domain is, if the vector field is irrotational, then the sign condition holds. That's a consequence of the maximum principle. So that happens only in the rotational problem. So the construction of the solution in the without surface tension, in our approach, what we did was we construct solution with surface tension first, and then take the limit as surface tension goes to 0, because we do have the estimate with the vanishing surface tension coefficient. But in other ways of construction, people could construct the solution without using the vanishing surface tension limit. And for the compressible fluid, we could try. So in a compressible fluid, the difference is that the configuration space is more like a space of diffeomorphisms without any constraint. And then there is additional potential energy on the density, on the variation of the density. Or in other words, it has something to do with how the fluid is compressed. So one can try that, but we didn't do that. There had been several work on that, but probably using a different approach.
I mean, that made me think about your comment earlier about how you can get incompressible from a limit of compressible fluids, where compression is energetically very expensive. But these limits can be very, very complicated. I mean, I remember Ira Herbst in Virginia talking about all the strange things that can happen even in simple mechanical models when you try to do that.
Yeah, but the complication mainly happens when so this is like in the mechanics, this is like the penalization problem. And there is an issue of the initial velocity, whether that's tangential to the constrained manifold or transversal to the constrained manifold. And the complication mainly appears in the case of non-tangential initial velocity. And so here, if you take compressible equation, but with very close to divergence-free initial velocity, then the proof is not that bad. But one could do that without this approach. This is just a conceptual way to show you that this is same as those mechanical problems with like a strong elasticity. But that's the idea behind Eben's work in the 70s.
Are there any more questions in the audience? Any comments? If not, I'd say we gave a big round of applause to Chongchun and to all the other speakers of the summer school.